there's two subjects left in the course now. One is a kind of a brief introduction to some air pollution issues. And I really narrowed that down. We're just going to pretty much talk about the two ozone problems. I'll explain what I mean by that in just a minute. And then the last subject of the course, which will come after break, will be renewable energy. We'll look at how environment and energy connect together. So if you go on the EPA website, they've got a list of all the different air pollutants that they are concerned about. And this is roughly their list. I've combined a couple of things, but this is roughly their list. It's a big list, and of course, every one of these kind of has its own story, its own sources, the way it moves around in the atmosphere, the way chemical reactions may change these quantities in the atmosphere, and the way they impact human health are all different. So we can't possibly treat that complex subject in just a couple of lectures. But I just wanted to make a couple of comments about this. In general, this is what EPA is concerned about, and things are getting better. So for example, if you plot some of these concentrations on a relative scale, so this isn't an absolute scale, they're just calling everything in 1980, they're giving that the value of 100, and then plotting these quantities as they've changed since the year 1980. So they got nitrous oxide, sulfur dioxide, carbon monoxide, and lead. So I think you know some of these stories, right? So they took the lead out of gasoline, so that we're no longer getting tailpipe emissions of lead. They've put SO2 scrubbers on about half of the coal-fired power plants around the country. So that's been decreasing. And they've instituted this program of checking your car to be sure you are within emission standards. So the manufacturers have been asked to improve the vehicles in terms of how they emit NO2 and CO. And then you are required, at least I am required here in Connecticut, to occasionally get my car tested to see whether I'm within emission standards on this. So the combination of these different activities have brought generally the concentrations of these quantities down. And if we can thank someone, it's basically back in 1970, two important things happened. The Clean Air Act was enacted and the EPA was founded. So, I was doing some YouTube Googling the other day, and I found a celebration that took place last year celebrating the 40th anniversary of the Clean Air Act. And they were telling stories about the formation and the politics involved. And it was rather amazing because the Clean Air Act, which was a very powerful piece of legislation, actually passed the House and the Senate by very strong majorities, like 90%. In other words, both parties, Republicans and Democrats, voted strongly for this issue. And in fact, in 1990, when they enacted some changes strengthening certain areas of the Clean Air Act, again, both parties voted strongly in favor of it. Now that would never happen. It would never even come close. You couldn't get anything changed on this at the moment, except possibly pulling back on some of these regulations. So it's worth just thinking briefly about the history of this and the real impact it's had. Now, okay, so these aren't, some of these reductions are only by half and so on. And you'd like to have much stronger reductions than that. But still, it's a remarkable example of how scientists can identify a problem, work out the causes of the problem, and then the legislature can react to that and make some laws that help the situation in the long run over decades. It's nice to know that's possible, or at least was possible. this SO2 thing is big because that leads to acid rain. The SO2 is emitted from smokestacks. Coal has sulfur in it, so when you burn coal, you oxidize the sulfur, you get SO2. That goes into the atmosphere. Some of it forms small particles that get caught up in raindrops and rained out, but having SO2 dissolved in your raindrop makes that water acid, which has a big impact on the organisms and the soils and the rivers. And so we've seen actually a rather dramatic improvement in the acidity of rainfall, not shown on that last graph. Well, that last graph showed the SO2, but if you look at the acidity of rain that falls from the sky, that too has gotten less acidic over the last 20 or 30 years. So that's another side of that general success story. But what we're going to do here in this course is just look at these two problems, the two ozone problems. Ozone in the troposphere, especially in the boundary layer of the Earth, that is related to this problem called photochemical smog. It's an air pollution problem. And then the other problem is stratospheric ozone. And the problems here are different in their chemistry, different in the way they interact with the atmosphere, and they're also different in the most fundamental way. We've got too much ozone in photochemical smog, and we're worried about having too little ozone in the stratospheric ozone layer. So these are different in many respects, even though they all relate to the same molecule, O3, ozone. It's going to be the focus of both of these discussions. Stop me if you have questions. So a few things you have to know about ozone. Its formula is O3. It's just like the oxygen that you're breathing in, that's O2, but this has one more oxygen atom attached to it, so it's O3. Its molecular weight then, instead of being 32, is 48. It does obey the perfect gas law. It is a strong oxidant, however, much stronger than O2. If you put ozone in next to some organic substrate, it will immediately attack that and try to oxidize the substance that it's touching. It also has important radiative properties. It's a greenhouse gas. It can absorb and emit infrared radiation. That's not surprising because it has a dihedral structure, oxygen, oxygen, oxygen. So as it vibrates, it can absorb and emit long-wave radiation. In addition, though, it can absorb ultraviolet radiation, much shorter wavelength. It does that by pushing electrons up and down in their orbitals. And these are both important for us. Lifetime in the troposphere is typically pretty short, hours to days. Lifetime in the stratosphere is quite a bit longer than that. Usually it's in years. I'll be defining something called the Dobson unit, which is the way we measure the total amount of ozone in a column, going all the way up and down through the atmosphere. It's one of the common ways that we talk to each other about how much ozone is in the atmosphere. And as I've indicated, in the troposphere, we're interested in photochemical smog in the boundary layer. In the stratosphere, we're interested in the ozone layer. So if you plot the amount of ozone in the atmosphere versus altitude, the altitude scale is in kilometers. Now, this unit here is millipascals. So what I've plotted is the partial pressure of ozone. You know, when you have a mixture of gases, every type of molecule contributes something to the total pressure of the gas. And so this is the amount that the ozone mixed into the atmosphere contributes to pressure, but it's a small amount, so we're representing it in millipascals. That is 1,000th of a pascal. And so you see a little elevated ozone in the first kilometer or so of the atmosphere, and that's the subject of one of the discussions today. And then, of course, you get this rather large peak in ozone concentration up in the stratosphere, peaked somewhere between 20 and 30 kilometers. That's the ozone layer. Questions on that?
What accounts for that peak?
Well, so there's a formation process going up there that involves ultraviolet. I'll talk about this later, but I'll give you a preview of it. There's ultraviolet radiation coming from the sun that will dissociate a regular oxygen molecule. So you start with an O2, you break it into two O's, and then it'll recombine in some cases as two O3 molecules. Usually that's short-lived, but when I get to that section, I'll talk about how it recycles, but then goes back to ozone. But it has to do with ultraviolet light being able to reach those elevations. It's a bit complicated because ultraviolet light is also involved in its destruction. So we're going to have to take a careful look at that when we get to that point. So for the moment, we're going to focus on this tropospheric problem. So we're going to be looking at this only for probably the rest of today's lecture. So some of the factors that are involved in photochemical smog are the amount of oxides of nitrogen being emitted. That's mostly NO and NO2. And they abbreviate that by calling it NOx. In other words, you can put a 1 or a 2 in there. There's also an abbreviation VOC, which is volatile organic compounds. It's like when you have a can of gasoline and some of it evaporates into the atmosphere. That would be an example of a volatile organic compound. Organic, means it has carbon in it. Volatile means it likes to go into the gaseous state. So a good example of that would be gas evaporating from your tank and going into the atmosphere. Sometimes you see RH, and this is confusing because we've been using that almost universally until now to mean relative humidity. But in this business, sometimes RH is used to represent reactive hydrocarbons. Reactive hydrocarbons. And in that way, it's almost synonymous with volatile organic compounds. The presence of an elevated inversion is going to be important because we want to know whether these emissions, the NOx and the VOC emissions, are going to be trapped and will be concentrated, or whether they will be diluted by mixing into large portions of the atmosphere. If there's a valley geometry, that's important too, because that also comes into the question of dilution. And then, as we will see, sunlight and warmth will be a factor because there are certain chemical reactions that convert one form of pollutant to another, and those typically require sunlight and warmth in order for those chemical reactions to take place. So if you're trying to understand why a particular part of the world has an air pollution problem, like the LA basin or Santiago, Chile, or Mexico City, it's these 5 factors that you want to look at that'll determine why one region has an air pollution problem, another region may not. It'll have to do with those things. We'll talk a lot more about those in just a moment. So Mexico City, for example, typically has this kind of haze. Now, looking at this, you wouldn't know, I guess, whether that is just a fog, a radiation fog, for example, except it's usually in the Mexico City area, which is in kind of a big basin. It's usually not found so much in other basins. In other words, so it's not just the fact that it's low-lying land and there's a clear sky and you're getting radiation fog. It has to do with these emissions of VOCs and NOxs that are then reacting to cause smog. Now, smog is a contraction of smoke and fog, but today it's used to mean a kind of air pollution with certain chemistry going on to cause that particular combination of particles and gases that are mixed in there together. Beijing has a similar problem, as do many other cities around the world. Now, EPA sets limits on ozone concentrations, ozone as a gas now in the atmosphere, and these have changed from time to time, but I believe these are the current values. There's a 1-hour standard and an 8-hour standard. So if you have an average ozone concentration of greater than 0.12 parts per million by volume for an hour, you are in exceedance of the 1-hour standard for ozone set by EPA. Even if you never reach that value, but if the average over an 8-hour period is greater than 0.01 parts per million by volume, you are also in exceedance of EPA standard. Yes?
Is this emission by like a plant or by a car?
No, this is concentration. So this is measured in the atmosphere. It's not what's being emitted. As we'll see in a moment, nothing emits ozone. So it's not, this certainly could not be an emission standard. Ozone is created in the atmosphere from other chemical emissions. So this is purely a concentration standard. So for example, the EPA in Connecticut would set up a station, used to be one here in Connecticut, I don't know if it's still here, and a few others around the state, where they measure ozone concentration in the atmosphere hourly, and they determine whether or not they are approaching or exceeding these EPA standards. Question?
So since it's not like one body that's creating this, like what happens when it exceeds? Like how does the city or the region limit it?
Yeah, we'll talk about that a little bit, but you can imagine it's confusing because you cannot track this down often to a single polluter. It's kind of a regional thing. Now, I've given this EPA standard to you, and they give it to you in 2 different units. And because we are familiar with such things in this course, I wanted to spend a few minutes just guaranteeing that you can work with both of those types of units. These are important numbers. So that's a part per million by volume, so that is a ratio of the number of molecules. That would be, let me multiply that by 1,000. That would be 1, 2, 3. That would be 120 molecules of ozone for every billion, because I multiply by that, for every billion molecules of air. Or if you prefer it this way, it's about 0.1. It's hard to split up a molecule, that's why it's hard to say it this way, but 0.12 molecules of ozone for every million molecules of air, okay? So that's in the form of a mixing ratio by number of molecules. This is a mass density. You'll recognize that unit, except instead of being kilograms per cubic meter, it's micrograms. A microgram is 10 to the minus 6 of a gram. So that's a pretty small mass density, but that is, again, a quantity that you are used to dealing with. So I want you to remember that. I'll do some calculations for you on the next slide. And we can do a similar check to be sure if these numbers are consistent. So on the next slide, I'm going to check to see if those two numbers are really the same, because we know how to do those conversions in this course. So a few ozone calculations. First of all, you remember that a mixing ratio by mass, where you're using rho, which is mass density in forming a ratio, can be computed if you know the mixing ratio by volume, that is by molecule, by just multiplying by the ratio of the molecular weights, which in this case is 48 for ozone and 29 for air. The mixing ratio that I gave you on the last slide was 0.12 parts per million by volume, which can be written this way. And so I'm going to take this equation and solve it for the mass density of ozone. So I'm simply going to bring the rho air over to the other side and plug in numbers. And that's the line here. So you still have the ratio of molecular weights. For the mixing ratio by volume, I've put it in here. And then I've put in a density for air, which is a standard value we've been using for sea level density all through the course. And that's about 1.2 kilograms per cubic meter of air. And you can check to be sure I've done this right, but when I convert this to micrograms per cubic meter, I get 235, which is just what the EPA claimed was the equivalent of that. So that's how you can go back and forth between these different measures of ozone concentration. Any questions on that? Let's do one other. Let's compute the partial pressure of ozone using the perfect gas law. Pressure equals rho RT. It's the partial pressure of ozone we're computing, so it's going to be the mass density of ozone we're using, the gas constant for ozone, and then the temperature, whatever that is, but it has to be in Kelvin. The gas constant for ozone is the universal gas constant divided by the molecular weight. That's 48, so it's a 173.2. And then let's just put the numbers in here. From the previous slide, 235, I've converted this to kilograms, though, so we get a 10 to the minus 9 in there. There comes the gas constant for ozone, and I've used a typical Earth temperature of 288, and I get 12 millipascals for that. So if the EPA had wanted to express that limit in partial pressure, that's the value they could have used. So we've seen three different ways that you can express this concentration of ozone. Let me go back to the plot. This was in millipascals, and this author had it about 5, but the value we computed is right about there, which is the same order of magnitude in units of millipascals. Okay, so who is an exceedance of this? And this gives you a rough idea. Now, this happens to be an 8-hour ground level ozone standard based on 0.06 or 0.07 ppmv. And they've got different levels here. 515 counties violate the 0.07 standard. 93 additional counties violate a 0.065 standard, and 42 additional counties violate the 0.06. But anyway, you see roughly where they are. Some are in Florida. Those are going to on vacation in Florida, watch out for this. It's mostly a summertime problem, but it's still kind of summery in Florida. Quite a bit of problem in the Northeast, and then of course California happens to be the worst for a combination of reasons. Large population, dense population, especially in the cities. There's a strong inversion that typically traps pollutants in Southern California. You've got mountains, which can often trap the pollutants from moving horizontally. So it's a combination of things that brings, and you have a lot of sunlight, which can help with the conversion to ozone. So that's roughly how the exceedances are scattered around the country. The damage, of course, comes when you breathe this in. It will then attack your throat, trachea, and lungs. It oxidizes organic tissue, which can really cause some breathing problems for some people are more sensitive than others, but we can all be influenced by this. And therefore, if you're an athlete, if you're a runner or something, usually you will keep yourself aware of the ozone concentrations and not do outdoor activities during periods of time when there's a high ozone concentration. Indoors should be okay because usually ozone concentrations inside a building are not a problem. The ozone will react with things in the walls, destroy itself, and you don't usually have much of a problem with ozone inside a building. But outside, you can, and you'll want to adjust your athletic activities accordingly. So now let's look at how the sequence of events that leads to ozone pollution. I've taken some slides here from a nice book by Turco, Earth Under Siege. So here's a little Volkswagen Bug or something perking along. And what's coming out of the tailpipe is primarily oxides of nitrogen, reactive hydrocarbons, and carbon monoxide. We're going to call those primary pollutants because they are being emitted directly by the offending vehicle. In addition, you've got the sun. You've got, with ultraviolet radiation, some chemical reactions are going to take place to produce NO2, some additional hydrocarbons, and then later in the day, we're going to start to generate these. Well, we still have the carbon monoxide, but now we're getting ozone, pan, which I'll define in a minute, and that haze that you see when you look at the pictures of these polluted areas. But this takes some hours to produce. And so this would, as I'll show you, this sort of thing would typically peak in the middle afternoon after some chemical reactions have converted the primary pollutants to these that we call secondary pollutants. I'm going to walk through these a bit step by step. First of all, the vehicle itself will emit these quantities depending on how it's tuned. So here's an example, fuel to air stoichiometric ratio. So in the old days, you actually had a control on the dashboard where you could lean the mixture or enrich the mixture. That is, how much gas goes in per amount of air into the cylinder. Now that's all done automatically by a computer, but still it's an important quantity. So the fuel to air ratio is given here, and you can't perfectly win this, because if you try to go for minimum carbon monoxide emissions, well, then you're getting more nitrogen oxides and so on. But you can see how the relative quantities of this may change, and you're trying to find some kind of optimum by getting the proper fuel to air stoichiometric ratio. And engines have improved greatly in this regard, and the catalytic converters have helped also. So then if you are set up a monitoring station, this was done in Lenox in the Los Angeles basin. I don't know where Lenox is. Anybody from LA? Must be some little suburb or something of Los Angeles. What's plotted here is the carbon monoxide concentration parts per million by volume for both plots. This goes through a typical day, a 24-hour day period, and this goes through a typical year. And in addition, they've got a summer and a winter curve here. So we can see immediately that for CO, there's more of a problem in the winter than the summer. And we see that here too, because November, December, January have higher CO2 concentrations than does the summer. We also see on the 24-hour clock, we see two peaks. What are those two peaks caused by? Rush hour, exactly. So this is primarily automobile emissions, and this is a primary pollutant. This is what's actually coming out of the tailpipe. So it reacts to the timing of the morning and the afternoon rush hour. So you can actually see that. Now, what makes the winter worse than the summer, I'm guessing, has to do with having a stronger inversion in the wintertime. And that will cause more trapping of the air, and the concentrations will build up to be somewhat greater in the winter than they do in the summer. So this is an example of a primary pollutant. Question on that? Let's go on and look at NO2. And generally, you can still see that twice a day peak. It's a little bit weaker. there's less of a difference between winter and summer because now you've got a combination of things going on. You needed some warmth, which you have in the summer, to convert NO to NO2, and you need sunlight as well. But then in summer you have a weaker inversion. So the two things kind of cancel to give you a more similar behavior between winter and summer when it comes to NO2. And now we'll do ozone, which is really the thing we're most concerned about. Ozone looks quite different than the other. Now it has a summertime maxima and a mid-afternoon. So that peaks around 1 or 2 or 3 o'clock in the afternoon. So we're not seeing the rush hour here because those primary pollutants hang around for several hours as chemical reactions driven by the sun and driven by the temperature convert them to the ozone product. And therefore, this is more dependent on those chemical conversion reactions than on the timing of the emissions themselves from the rush hour traffic. And look how peaked in the summer it is. That means that, again, this conversion is the big deal. Not the trapping by the, did I say it wrong? Not the inversion so much, which is stronger in the wintertime, but rather the conversion from primary to secondary pollutants are controlling the summertime maximum here. So if you're an athlete and you get up in the morning, that's great. Do your run right then before, say, 8 or 9 o'clock. If you're too lazy to get up that early, then I think you better skip it until you get to around, 8 o'clock in the evening, something like this, or even 9 o'clock. Then go out and do your run. Otherwise, do your exercise inside if you're in one of these locations. Questions on this? So this summarizes a little bit of that. The primary pollutants tend to peak in the early part of the day. The secondary pollutants peak in the later part of the day. Because of that, the time for those conversion reactions to take place. So an important part of the argument that I just gave you was this distinction between primary pollutants and secondary pollutants. Primary pollutants are the ones that are emitted directly. Secondary pollutants are the ones that are produced later on by chemical reactions going on in the Earth's atmosphere. So be sure you've got a clear distinction between those two things. Now, this has been well studied, and this rather clever diagram was published a couple of decades ago that has been very helpful in allowing city managers to reduce ozone concentrations. So what's plotted on this diagram? On the x-axis is the emitted reactive hydrocarbons. On the y-axis are the emitted oxides of nitrogen. Both the units are kilograms per square kilometer. I don't know what the time frame on that is. Perhaps it's per day or per year. I don't know. And then contoured on here is the resultant ozone concentration in the same units we've been using, parts per million by volume. So you recognize that as the 1 hour standard, that curve there, and that as the 12-hour standard from the EPA. So basically, we want our city or town to be somewhere in the periphery of this diagram, not in this high ozone concentration in the upper right. What this diagram shows you is that you've got two different control strategies. You can reduce the number of NOx emissions, which will bring you down on the curve, or you can reduce the amount of hydrocarbon emissions, which will bring you to the left of the curve. Now, if you are here it's not going to do you much good to reduce the hydrocarbon emissions because you're going to move that way on the curve and you're going to have about the same ozone concentrations. But if you reduce NOx emissions, you can bring yourself down to a lower ozone concentration. Conversely, if you're over here, your strategy should involve hydrocarbon emissions, not so much NO emissions. So this is a kind of a roadmap for air pollution districts to figure out where to put their effort in reducing emissions. Questions on this? But they've been doing this. This is, I think, for LA, but it's in relative units, so I can't say much about the units here. But it's 1965 to about 2005. And you see the carbon monoxide emissions have been decreasing, volatile organic compounds have been decreasing, and the NOx have been increasing. So these cities have worked very hard to reduce the sources of this, both from automobiles and from other industrial sources. Here in Connecticut, for example, we've had some success. This is the Connecticut 1 hour and 8 hour ozone exceedances in units of days. So how many days a year do you have an ozone exceedance? The data goes back to 1974. At that point, they only had the, which one is the lower one? That would be the 1 hour, yeah, the 1 hour exceedance. And that was about, if I average this out, that was about 50 days a year where you'd have an ozone exceedance in Connecticut. This data ends in 2004, but they were down to about 5 on average, about 5 days per year with an ozone exceedance. Now they have the 8 hour exceedance where you get more typically, although it's an average over a longer period of time, it has a lower threshold, so you get more exceedances. But that too has dropped over time because of pollution controls on the primary pollutants. Questions on that? So this can be done and has been done, but you know, it could be better. It could be better as well. And I think that, so that is that. I don't usually end this early, but I think I will today. So next time we will do the other ozone problem. We'll do the stratospheric ozone problem. So there is a little section on your book on this, so read ahead for that one.